Alright, so today we're going to be going over chapter 2 of this book again. This is No Nonsense Quantum Field Theory by Jacob Schwittenberg. So chapter 2 is covering basically the prerequisites, going over special relativity. Just as a recap, so we can have this in the forefront of our minds as we continue on with learning quantum field theory. Now, let's get right into it. So chapter 2 pretty much covers, again, special relativity, and it starts off by talking about space-time. Now, space is, if we think that space-time is fundamentally is a different mathematical object than space. And what do I mean by that? I mean that space can be depicted as mathematically as we have an x and a y coordinate system, right? And we can pick any point in the space, right? So we could pick any point here, and each point represents a location in space. We can do this in 3 dimensions also. So we have our x, our y, and our z, and these are all spatial coordinates. So these are all ways to depict space. So now, how do we depict space-time? This is 4-dimensional. So we're gonna see this quite a bit actually. You also might see this in general relativity courses, where we compress down 3 dimensions. So we can't really talk about or think about or conceptually understand 4 dimensions. But what we can do is we could say our axis is our t-axis. And so this is time. And at every moment in time, let's do it like this. And here's our 2 other dimensions. We have our x and our y dimensions, say. But we also suppress our z dimension sort of in this plane. Right, so you can't really see the z dimension, but it's there nevertheless. We can only really depict 2 of them. So the 2 that we're depicting are the x and the y coordinates, and then our t coordinate is our time. And so you could sort of think of this as at every moment in time, we're taking, at every slice in time, we have spatial coordinates, right? So we get to think of this as, say, we take at time, say, 1, we have a plane that looks something like that, right? And this is our plane, our spatial plane. We can do the same thing at time, say, equals 5. Say our time is measured in seconds. So at time equals 5, we have a spatial plane also. And this is our spatial plane at time equals 5. And we can imagine how 2 events might look like in the space-time. So say we're at this location here at time equals 1, and we're at this location here at time equals 5. So we mapped out this trajectory. Make that all straight. It doesn't have to be straight, right? So at time equals 4, we could have been somewhere in here, right? At time equals 4. In that case, our trajectory would look like that. we could say at time equals 3.5 or 2.15 or something like that. We could have multiple trajectories in here, right? So nothing's stopping us from having different paths that take us from one point to the next in space-time, right? So these guys here are examples of depictions of space, or representations of space. This is what we're calling space-time. Now, here's the thing. In space, we can understand the notion of distance as through the Pythagorean formula. So say this is our ds, our distance. Our ds squared is equal to, so here's our x component, dx. Here's our y component, dy. And say we also have a dz in here. If we had a dz component, it would be x dx like that, plus dy squared plus dz squared. And we can do this in multiple dimensions, right? We can say that ds squared is equal to dx squared plus dy squared plus dz squared plus dg squared, and we can go on and on for d dimensions, right? So oftentimes this can also be written as a summation, right? A summation of, and this will be useful when we talk about general relativity, is delta xi times delta xj, where delta xi can equals, where I can refer to the y component, the z component, depending on what number I is. We're getting a little bit too far astray here, but depending on what number I is, this is more, these are more labels, right? So instead of maybe saying dx's, I could say, I can only think of x off the top of my head for right now, but I hope you get the point, right? So we're summing over I and j in this case, and we're going over d dimensions. This is the same thing. We'll go over this representation later when we talk about general relativity, but nevertheless, we can generalize in 4 dimensions. We can generalize to 5 dimensions. We can generalize as much as we can, but when we're talking about space-time, it's a little bit different. Space-time, I believe it was Einstein, people like Einstein and Minkowski speculated that the structure of space-time was actually different than the structure of space itself. The idea was when you merge time in with the picture of space, then our metric, as they would call it, or our notion of distance, was equal to dt squared minus the spatial components, so dx squared minus dy squared minus dz squared. Right, so this has a positive sign on it, while these guys here had negative signs, or have negative signs. The idea here is that these have to be the opposite, right? So the time component can have a negative sign, but if the time component has a negative sign, then our spatial component would have the positive signs. So this is just convention. You'll see this written in different ways. This can also be dt squared plus dx squared plus dy squared plus dz squared like that. This is also okay. So these are this is a structure of space-time, and this is fundamentally different than the structure of space itself. The idea, again, is that when we put time into the picture, our metric, that the notion of distance actually changes. And we'll see how this is useful and how this will become helpful later on. Right, so we've talked about space-time. This is sort of the arena of physics, is how the book talks about this. It talks about, this is roughly from page like 38 to like 42, where we're talking about structure of space. So the next thing to cover would be the speed of light, right? So the speed of light is interesting because now we're going to be talking about time dilation. So time dilation, so we want to keep this notion of distance in the back of our mind when we start talking about time dilation, because we're going to come back to it very quickly in the book. The notion of time dilation goes roughly as following. Suppose you had a particle of light, or just a particle. Say it's a random particle, and it is traveling between two mirrors, right? So say in this case, it doesn't travel in the x direction. It doesn't travel in the y direction or anything like that. It just is still bouncing between two mirrors. In the book, the author talks about a person I believe is throwing a ball or something like that. Or he actually has a pulse of light, right? So the person, he's holding this little flashlight, and the flashlight takes some time to go a distance L between, this is at point A, this is point B. So the distance to go from point A to point B is L, and from point B back to point A is L. So the total distance traveled is 2L. Okay, and if we're talking about a particle of light, then we're going to want to talk about the rate of that particle, which is c. So in the case of light, the rate is c, which is, again, if you don't know this, c is the speed of light, and it's measured to be roughly 3.0 times 10 times 10 to the 8 meters per second. Now, this is speed of light. This is the time it takes for the light particle to go from point A to point B and then back to point A, right? Without it moving in the x direction. So we'll call this still, delta t s, or subscript s is the amount of time it takes for the light to travel between two mirrors. And so that's page 45, and this is all fine and good. We're understanding the time duration between two positions of speed of light. But now we want to consider the following. We want to consider what would happen to this time if our particle of light now looks like this. It's traveling in the x direction. So if our particle of light is traveling in the x direction, well, we could say if we bifurcate this like so, such that we have a 90-degree angle, we can work a little bit easier with this. Well, the distance from here to here is still L. right? The distance, the total distance traveled is going to be this plus this, right? The distance between here and here is going to be, the distance between here and here is going to be the rate times the time, right? So the rate of the particle, so it's traveling in the x direction. There's a little bit of it traveling in the x direction now. So we'll call that rate of travel in the x direction u, and we'll call the time it takes, because remember rate times time gives you the distance that it's traveling in the x direction. We'll call that dt moving, right? Because it's moving in the x direction. You can do it for the y direction, you can do it for the z direction, and so forth. Right? The distance, so this distance here, again, so how do we calculate this now? Well, from here to here, well, that's going to be 1/2. Oh, I don't know how that got to be red. That's going to be 1/2 u t moving. Right, so that's going to be, so this here is the distance from here to here. Right. And I'm just going to move this a little bit so I give myself some space. And the distance between here and here, right, well, that's going to be a Pythagorean formula, right? That's going to be, if we call this L, little l, which is I think what they call it in the book, then little l is equal to this squared plus L squared, big L squared. So little l is equal to that. Well, so L, therefore, is equal to the square root of 1/2 u delta t moving squared plus L squared. And since we have two little l's, because we're traveling between this here and here, and then here to here, this is just that times 2, right? So the total distance, we'll say total distance traveled is equal to 2 times all of this. So 1/2 u delta t moving squared plus L squared. All right, so this is all fine and good. Let's keep this in the back of our minds. Also, we want to keep this in the back of our minds. So maybe I will box this right here. And so what do we have? We have a total distance, the total distance traveled for the particle that's moving in the x direction. So I rewrote this total distance right here. This is what we got when we were down here, when we were talking about the total distance that this light particle travels as it goes from point A to this new shifted point B. It's shifted in by delta x, and we're going back to point A on the mirror. And so I rewrote that, and that's up here. I want to talk about now how we can understand, or what we can do with this. Basically, the total distance, again, is So the total distance is the rate times the time, right? So we could say that the rate of the, say it's a light particle, right? So the rate of a light particle times time. Now, again, this is equal to 2 times 1/2 u delta t moving squared plus L squared. Keep in mind that u can also be c, right? But u is strictly a rate in the x direction, right? So, and we can take, when we get to the punchline of this, we can take the limit as u approaches c and see what happens to our result, and we'll see exactly how that works. So we can manipulate this a little bit. So this is t moving. This is the time moving in the x direction. We can now basically kind of just massage this a little bit. We can say that, so I'm kind of just following the derivation on page 47 here, but I'm sort of talking about it in words as well, so we can understand if there's any confusion in this derivation, you can refer to this video. So we have that we can square both sides, right? So if we squared both sides, we would get c squared delta t m squared equals 4 times, not the square root because we're squaring everything, 1/2 u delta t moving squared plus L squared. And what I want to do now is I basically want to take everything to one, I want to isolate t moving. I want to see what happens, right? So if we have, so we can basically say now that c squared delta t m squared equals, so this part right here, what's this going to be? So this is going to be 1/4 times u squared times this squared, right? And then this is going to cancel out with that 4. So we're going to get u, how do I want to do this? Oh, in there, in the book, they actually just take the 4 over. Let's do it like that. So we divide both sides by 4, right? So it's going to be c squared t, or delta t, not 2 deltas, delta t m squared over 4 is equal to 1/2 u times delta t m, all that squared minus L squared. Now we want to take this guy over. We want to subtract that because we want to get the delta t moving on both sides of the equation. We get c squared times t delta m squared over 4 minus 1/2 u u delta t moving squared equals L squared. And if we were to keep on going with this, we can extract t moving out. So that, again, the aim here is we're trying to isolate what the time duration is as this particle is moving. And so this is going to be c to the 4th over 4, or c, not to the 4th, c squared over 4 minus 1/4 times u squared. So that's kind of just u squared over 4. Okay. And that's equal to L squared. Right, so now we can multiply or divide both sides by this right here. So if we divide both sides by that, then we've officially isolated Tm squared. That's going to equal L squared over C squared over 4 minus U squared over 4. I'm going to erase some of that. And I'm actually going to take the L squared center it a little bit better. So we're getting there, right? We're getting to a point where we're going to be able to compare what Tm is in terms of Ts, right? So remember, Ts was right here, right here. So we're going to be able to compare these two. We're going to be able to see how one relates to the other. We're on our way to doing that, basically. Okay, so what can we do what can we do now? Well, we can say, if we want to get rid of some stuff, which we can do, we can multiply. And you know, this wasn't like a set out protocol. We want to keep this in mind, that this wasn't really like a do this step and then do this step and then do this step, when people were sort of going through this for the first time. People like Minkowski and Einstein and all these people, they were manipulating equations sort of at their leisure, trying to figure out if they could find, apologies for the light from the sun coming in. Let's see if I can change this up a little bit. It's fine for right now. There we go. Anyways, I'm not going to do that. Anyways, we can talk about, we'll be able to compare these two. So what we can do now is basically say we can multiply both sides, or this side by 4 over c squared and 4 over c squared. Right, so if we multiply both sides by 4 over c squared, we're going to multiply it by that and by that. And what we get, right, so when we do this one, right here, we are going to get c squared over 4 times 4 over c squared. It's just going to be 1. Everything's going to cancel. And then in this case, it's just going to be u squared over c squared. Right, so what we're going to get, now I'm going to rewrite this a little bit, not in red, in black. I'm going to get Tn squared equals 2L over c squared. That works, right? Because when the squared gets applied to the L, we're going to get our L squared. When it applies to the c, we're going to get the c squared. And when it applies to the 2, we're going to get the 4. And there's going to be a reason why I'm doing this. And you'll see, if you take a look over here, that's right here. Right, so hint, hint, we are getting there very quickly. Now, we're going to get 1 minus u over c. That. Right, we're almost there. We could say, we could take the square root of both sides. So if we take the square root of both sides, we get delta Tm equals this squared. Well, this is just, remember, this here is just Ts. Right? I just alluded to that right now. So this is delta Ts, and then we take the square root of all this down here. So 1 minus u squared over c squared. Right? Where oftentimes, we'll definitely see this oftentimes, the denominator here, this square root of 1 minus u squared over c squared, is going to show up a bunch. We're going to call that gamma. And gamma is going to look like, as you, we can imagine now, we can imagine what this would look like. We can imagine what this here would look like, what our gamma would look like in the case when u approaches c, right? So what we could, let's for kicks, let's do that. Let's do the limit. What would the limit as u approaches c be of Tm? What would that equal? Well, if u approaches c, right, so if u here approaches c, we're going to get 1, we're going to get 1, and then we're going to get 1 minus 1, which is 0. Square root of 0, well, can't really do that, right? Square root of 0, that's 0, and if you have a denominator of 0, then this is going to be, you can't do this. So there's an upper bound, basically, is what we're doing. We have this upper bound now, where if u, as u approaches c, it gets closer and closer to 1, right? And we're going to get 1 minus that, and as we get closer and closer to 1, we get to this sort of delta ts over infinity, or over 0 actually, over 0, which isn't going to work. So this isn't going to work. And so we have, so this is the relationship. So this here is the relationship that we're looking for. And this is going to be really useful when we start talking about proper time, which is mentioned in the book, and which is what we're going to cover right now. All right, I just want to make a small correction that I noted. So gamma, this thing right here, it's actually 1 over. So 1 over that is what's going to be recurring throughout the special relativity playlist, and we want to keep this in mind. And again, so we're noting here that right here that as u approaches c, right, so as the distance, as our velocity in the x direction approaches the velocity of light, we get this 1 over 0 effect, effectively saying that we can't have anything be at the speed of light. We can have something be at 99% the speed of light, but we can't have something be at the speed of light. And this is gonna be crucial in understanding exactly what proper time is, which is what the next section here is going to cover. And so this, again, this occurs in, this is section 2.5 in the textbook. Again, if you don't know, I'm going through this no-nonsense quantum field theory textbook. We're on section 2.5, and we're talking about proper time now. Before I talk about proper time, though, I want to take a little bit of time to just look at this gamma factor a little bit more, because I think it's interesting, right? So we can plot, for example, this gamma factor as a function of u, say, and have everything else be a constant. So if gamma is a function of u, which it clearly looks like it is, then what does it look like? Well, what does this, what exactly does this gamma factor look like? Well, as u increases, right? So u is going to, if u is really small, right? So if we have, if u here is really small, what is our gamma going to be? Well, if u, okay, so if, let's take this, let's look at this point by. So if u is small, then that means this is going to be small, right? We're going to have 1 minus a small number, right? So 1 minus a small number is close to 1, and then the square root of that is going to be small, right? So, and effectively, what we're going to get if we plot this out is that it's going to u is going to start off really small, but then it's going to start getting bigger and bigger. And as u gets bigger, the effect of the denominator is going to make it, is going to make this sort of blow up, because we're going to have the square root of a really, really small number, right? Something small in the denominator is going to result in something big, right? So we're going to get a plot that looks something like that, right? So as we increase as we increase our value for u, or the speed at which we're traveling in the x direction, or the y or the z direction, as we increase the speed in that direction, then our value for gamma is going to increase, right? If we can write this out, so if u is a function of, or if gamma is a function of u, it's a weighting factor on delta s, right? Because we have here that our delta s, this equation effectively is gamma. It is gamma divided, or times the still, what the time would be if the object was still. And what we get is that, again, this is time dilation. So if u increases, this is going to increase. And so our delta Tm is going to be a stretching, is going to be a largening, if you will, of T delta S. Right, so this is sort of the equation in its entirety, and this is time dilation, right? Where gamma is this factor right here. It's a function of u, and we have this is our time dilation equation. This is how time dilates as we speed up in the x, y, or z direction. Let's talk about proper time now, because this is going to be interesting. So proper time is, in the book, he actually uses a very good example, I think, to get at exactly what proper time is. So we're going to consider someone still, right? And we want to come back to this idea of right here, right? So this is our what's called a metric, right? We can call this a metric, we can call this a distance. So let's calculate the distance for someone who is not moving, right? So we've calculated the with the time dilation equation. We've determined what the time dilation equation is, and we can now, let's plug the time dilation equation into here. But first, before we do this, actually, we need to correct the units a little bit. So delta S squared, we're going to have to multiply this by c squared delta t squared. And then we have our plus delta x squared plus delta y squared plus delta z squared. So we're at this point. Again, my apologies for the dog barking. I quickly stopped the video, if you could tell. But anyways, so we have this is our metric now. Everything's in the right units. And so what we want to do now, what I want to do is we now want to dive into this idea of proper time. So proper time, again, we want to try to find a time frame by which the moving frame will give us the same duration of time as the stationary frame, or the still frame. And in order to do that, we have to use this new time dilation formula, right, that we got right here, because the original still time is not going to cut it for us, and we'll see why. Let's take a look at why that's the case. The reason that's the case is because if we take the still frame of reference, which is replacing this merely with 2, or with, if we just go back here, we replace it with 2L over C, right? We're going to get 4L squared over C squared times C squared. And since we're not moving in any x direction, we're going to get delta S squared of, well, that's just going to be 4L squared, right? So that's going to be 4L squared. That's all fine and good. But what about when we're moving in the, the x direction? Well, if we're moving in the x direction, the only way to get a similar length is to use our time dilation formula, right? So instead of TS, we're using TS in this case. Instead of using TS, let's use TM. Right, so if we use TM, we're going to get that delta S squared is equal to C squared times delta T. Well, if we're going to use, we're going to use delta TM this time, the moving frame. And what's that going to be? That's going to be, if you can follow here on page 49 also of the book. We're going to put in our original formula that we got. We're going to, this one right here. If we put this one in right here, with the exception of, we're going to modify this a little bit. This is delta x, right? So, because time times rate is a change the change in the distance. So, what I'm going to do here, let's see. I'll just do it like this. So that's going to be 2 times the square root of 1/2 delta x squared plus L squared over C, right? So that's, and we're dividing by C in this case because we want to, this total distance here, this is, I'm trying to see if I wrote it somewhere else, but anyways, the total distance is going to be the time times the rate, and we're just going to divide both sides by C. Because this is a time unit. This right here is a time unit. And then since we're moving in the x direction, right, let's take a look here really quick. Since we're moving in the x direction, we need this right here also. So plus delta x squared. Right. And now that I am looking at this, I'm realizing this has to be a minus. And these guys have to be minus also. Those are minus signs. Because we're looking at this non-trivial structure of spacetime. So we can kind of see now, we could see, okay, well, and this has to be squared. So we could see that the C's are going to cancel. We're going to get a 4. We're going to get this is going to equal 4 times 1/2 delta x squared plus L squared minus x delta x squared. Now we could see here, 4 times 1/2 delta x squared, well, that's going to be 4 times 1/4 x squared, right? So that's just going to be x squared. So that's going to be delta x squared. We're going to get plus 4L squared and minus delta x squared. This is all just algebraic manipulation at this point, but we can see now that this is 4L squared. Well, if we take a look at this and we take a look at this, we can see that we're getting the same answer. So what does this mean? This means that time dilation, or the time dilation formula, works in moving frames. The time dilation formula tells us, or it gives us the opportunity to render everything invariant, even if we're moving. Right? So we have to use a time dilation formula in order to preserve distances when we're moving in the x, y, or z direction. That's what this is telling us. Because again, and we also, again, we have to use this non-trivial structure of spacetime. Now, I don't want to go on for too long. So what I'm going to do is I'm going to split up these videos, split up chapter 2 maybe, into a longer, or into shorter videos. So we've gone over time dilation, we've gone over a non-trivial structure to spacetime, we've gone over a lot of special relativity. So we're in the next video, we're going to go over probably the remainder of chapter 2. The remainder of chapter 2 is going to talk about 4 vectors, Minkowski metrics, and all this fun stuff that is going to launch us into more advanced stuff so that we can get into quantum field theory. So I'll see you guys in the next one.